Question 4. We have a 40 kilogram box. It's initially at rest. It is pushed 5.8 meters along a rough horizontal floor with a constant applied horizontal force of 145 newtons. If the coefficient of friction between the box and the floor is 0.3, find the following. Okay, so we have a non-conservative force involved. There's friction involved. We have a constant applied force, so we definitely know we can't use energy conservation for some of this. And we're going to have some work done because it was pushed a distance. All right, so for part A, we just want to find the work done by the applied force. All right. Well, work by the applied force. We can do it down here. I want to make sure I get the question in there. We know that all work is just force times the distance times cosine of the angle between those two. So this is always the angle between these two values. They're both vectors. If we're going to plug in the applied force, well, then we just do work is equal to, for F, we want to use the applied force. And it told us here that we did a constant application of 145 newtons. So for that, I'm going to put in 145. Change in R, that's how far we pushed it. So for here, I'm going to put in 5.8. 5.8 is how far we pushed it. And cosine theta would be the theta between these two things. Well, it said we applied a horizontal force and we pushed it on a horizontal floor. So we'll have the cosine of 0, which is also just 1. All right, so this made it easy. We'll just do 145 times 5.8, and we get an answer of 841 joules. Okay, not quite sure how I got 840 here. You'll see it in your homework as 841. Part B comes to the increase in internal energy in the box floor system due to friction. So this is internal energy that we can't get back. This is heat, okay, that gets put into the system due to friction. So for that, again, we need to use work. We need to figure out that energy, but we'll be using the non-conservative force of friction. So we'll have W is equal to, the force we want to use would be friction. So the friction force would be mu Fn. Okay. Change in R again. We moved it 5.8 meters. And cosine theta. So cosine theta for friction is always 180 degrees because it points backwards against our horizontal floor. There's a few other things that we know. We can start plugging in. Mu in this case was given as a 0.3, so 0.3. Normal force in this, if we did a free body diagram and we're pushing across a horizontal floor, you'll see that Fg is equal to Fn, which is also equal to mg. So the mass of the box is 40 and g is 9.8. So that's our Fn. Distance here would be 5.8, distance we traveled, and the cosine of 180 degrees. So now we just plug that in. We'll have a 0.3 times 40 times 9.8 times 5.8 times the cosine of 180 is a -1. And so this gives us a negative 682 joules. Okay. So this is always the work that we have lost. Okay, so right, the friction force is always the work we have lost. Where did we go? Where did it go that we weren't able to get it back? Well, it went into heat. It went into the box floor system. We put heat into it. So here it's negative, saying we've lost it. But what we've done is we've increased the amount of heat in the box. Okay, so that's why you'll see in a positive over here. We have increased the heat in the box floor system because we have lost this amount of energy from this motion to heat. Let's look at the work done by the normal force. And I have it here as 0, but why? Well, when we plug in, okay, we'll use the normal force. We know the normal force is mg. So just like over here, the normal force would be 40 times 9.8. So this would be the normal force, mg. Change in R, that always remains the same. That's 5.8. And cosine of the angle between the two. So normal force if we were to draw out the free body diagram, force of gravity is pulling down, normal force is pointing up. Here we have our acting force pulling the box. Here we have our friction force denying our motion as much as it can. Okay, and overall movement is horizontal. So this is going, what's the angle between the normal force and the change in R? And we can see that those are 90 degrees apart. And as soon as we put in a cosine of 90, this whole thing turns to 0. So why is the work done by the normal force 0? Because of that 90 degrees. Okay, anything that's 90 degrees apart does no work. So it's 0. No work has been done. Same here, the work done by the gravitational force. Gravitational force points downward. Delta R is in the x direction. X's and Y's don't mix in here. So again, this one is 0. Why? Same reason. Cosine of 90. Okay, cosine of 90 is also 0. So it kills it. I'll let you write whatever you want. You can give me a one-sentence deal there as to why. Why is it 0? Use your own words. Let's look at E. What's the change in the kinetic energy of the box? So you see we've done all of our forces now. A was the acting force, friction force was part B, C was the normal force, D was gravitational. So we've done all of our forces. What is the change in the kinetic energy of the box? All right, well, we are putting in 841 joules. Friction is taking out 682 of those joules. Okay, so the change for the kinetic energy, remember there's no gravitational potential, there's no spring potential, so the leftover must be kinetic energy. The change in that kinetic energy would just be the one minus the other. So let's go 841 and minus 682. And we get 159. Okay, so we get 159 as the change. Go 841 minus 682. Yeah, that's how we get 159. So now part F, we need to figure out what the final speed of the box is. Okay, to find out the final speed of the box, we have this much energy to use. Okay, initially the box was at rest. Let's take that and put it into kinetic energy. So that's the change in the kinetic energy. Okay, so for that, let's look at change in kinetic energy. Change in kinetic energy, which is also another form of work, right? Change in energy. Energy is 1/2 mv final squared minus 1/2 mv initial squared. Final minus initial. Initially, this box was at rest. So that goes to 0. So we have that the change in kinetic energy is simply just the final, 1/2 mv final squared. So the amount of work that we can donate to this change in kinetic energy is 159. 159 joules must be put into 1/2 mvf squared. Okay. Now 1/2, the mass was 40, and we are looking for final squared. So half of 40 is 20. Take 159, divide it by 20, and then take a square root of your final answer. And we should get a VF of 2.819. So I'm going to go ahead and round that to 2.82. And that's how we get the final answer of 2.82 meters per second.